Silica optical nanofibers for the realization of pollutant sensors in water. Optical fibers. They're like hoses, but instead of water, they carry light. They have 3 layers, a coating, cladding, and a core. For this project, we use SMF28 fiber, with the properties shown. Now let's take the fiber and stretch it, until its diameter is roughly the same as visible light wavelengths. In the nanofiber, the light is strongly confined, and the optical field presents a tail surrounding it. This can probe the external medium and be used as an environmental sensor. However, this stretching creates dangling silica bonds at the surface. Light interacts with these bonds, causing an absorption of energy, thus a rise in temperature, which is where I come in, to study the thermal effects. We perform 2 types of measurements: distributed, where we measure the temperature along the nanofiber and its tapers, and static, where we measure the temperature at one point with varying inputs of power. Both tests were done using an infrared laser and a green laser to study the effects of wavelengths. The optical setup is as shown. The nanofiber is mounted on a translation stage, and a thin thermocouple is used to measure the temperature via contact. For the distributed measurements, with the infrared laser, we found a symmetrical relationship between the fiber diameter and the temperature. With the green laser, we found an asymmetrical relationship, with higher temperatures near the input. For the static measurements, both lasers using the average result showed a positive linear trend. In general, thinner and shorter fibers heat up more, as expected by the theory. For the next steps of the study, we aim to calibrate the temperature measurement. For the moment, we only have relative measurements. We started testing this near the end of my internship, though it is still ongoing work. The targeted application in the group is to use the evanescent field to probe the surrounding medium, such as polluted water. The interaction of this field with pollutants can alter the original spectrum of the laser by adding new wavelengths, which are the spectral signatures of the pollutants.